My talk is on AMIGO, Astrodynamic Middle Frequency Interferometric Gravitational Observatory. This work is with Wang and An-Ming. First, I review various middle frequency gravitational wave activities. I then talk about the mission concept, noise spectral density, and the sensitivity of AMIGO, AMIGO Orbit design, and the time delay interferometry. There are two ways to implement AMIGO. One is using constant arm option, the other is using geodesic option. A geodesic option, the orbit varies, the arm length varies, so we need to use time delay interferometry. For constant arm, we need to use microthrusters to prepare it to have constant arm. The goals of middle frequency gravitational wave detection is to detect intermediate mass black holes at a few billion light years away or further, to detect galactic compact binaries as well as stellar mass black hole binaries like gravitational wave 1150914, the first event of advanced LIGO. Alert laser interferometers days before merger by detecting inspiral phase and predict time of binary black hole coalescence and neutron star coalescence for ground interferometers. The last goal is have a possibility to detect radic inflationary gravitational wave background. Massive black holes grow from smaller black holes, and the way it grows depends on seed of black holes. So intermediate black hole population and activities is important to understand this chain and to understand the galaxy growth. The various middle frequency gravitational wave mission concepts are the Cassini, which is already completed. On the top of the right diagram, interplanetary network of optical lattice clock. Their goal is also plotted on the medium top of the right diagram. Torsion bar, advanced SOGRO, superconducting omnidirectional gravitational radiation observatory. MEGA, metal wave interferometer gravitational wave antenna. ZIGA, Zaosan atom interferometric gravitational antenna. AMIGO, DO, and DCIGO, MIDGO. The arm length for AMIGO is designed to have 10,000 kilometers or a few times more, and laser power is 2 to 10 watts or a little bit more. Accelerated noise, assuming these are pathfinder noise. There are 4 options which we studied. All of them are laser-like formations. First, Earth-like solar orbit, which is the chosen option for AMIGO, which is 3 to 20 degrees behind the Earth orbit. 600,000 kilometer high orbit around the Earth, 100,000 kilometer to 250,000 kilometer high orbit around the Earth. The last one is near Earth-Moon Lagrange point, L4, Earth-Moon L4 and L5 orbit. And the scientific goal we have already stated. sensitivity, the baseline sensitivity is for 2-watt emitting laser power and the 300 millimeter Phi telescope. The design sensitivity for AMIGO is 10-watt emitting power and the 360 millimeter diameter telescope, or a little bit less power, but with 500 millimeter diameter telescope. So the sharp noise for strain gained from this design is 10 times more than the baseline sensitivity. The AMIGO solid curve shown in the last page diagram is the design sensitivity for AMIGO. The strain power, density, amplitude was the frequency for various detector and gravitational wave sources is shown below. The solid blue line is for AMIGO. The dashed blue line is for baseline AMIGO. For the orbit design, with Earth-like solar orbit, we have the arm length. For the geodesic version, we have the arm length varying by 0.5%, plus minus 0.5%. So the arm length variation is about plus minus 50 meters. And the Doppler velocity between two spacecraft is below plus minus 0.02 meter per second. For 50 meter arm length difference, the Michelson interferometry cannot reach the sensitivity goal because of laser frequency noise. So for geodesic version of AMIGO, we need to have time delay interferometry to have a few links matched together to make two passes almost equal. So in the picture, in the diagram below are the passes for XYZ, Michelson, relay, beacon, and monitor. And the TDI requirement for AMIGO is 0.1 meter between two different path lengths, or 330 picoseconds in time between arrival time. So our first generation TDI have two paths differs by below 10 picoseconds. So all of them satisfy the requirement for AMIGO TDI. And this is the table for first generation TDI for not just the solar orbit AMIGO, but all for others. All others also satisfies the TDI requirement. And the second option is constant arm option, which seems viable according to technology development until now. For the solar orbit 8 to 12 degrees behind the Earth, the required acceleration is 15 nanometer per second, and thrust requirement is 15 micronewton, and the propellant requirement is only 0.05 kilogram out of 1,000 kilogram total spacecraft weight. Currently, a number of detection methods are proposed and under active research to bridge the middle frequency band gap between Earth-based and space-borne gravitational wave observations with important science goals in this band technique limit will be extremely challenging to overcome for Earth-based detectors due to Newtonian noises. We propose a first-generation middle-frequency emission concept AMIGO with 10,000 kilometer arm length. The technique's readiness level is high. The sensitivity is good to reach science goals considered in the last section. If a Pathfinder mission is designed with 2 spacecraft demonstrations of ranging in the solar system for a LISA-like mission, the case with 2 to 5 degrees lagging behind the Earth's orbit choice could be considered. Just take one arm of this AMIGO case. It would be good to test many things in the solar system: deployment, both radio and laser communication, noise budget, and the drag-free system, together with a concentrated effort on distant metrology. It might be simpler than go to L1 or L2, some Earth Lagrange point. Thank you.